Good morning. Can you hear me okay in the back? Yeah? Okay. Well, on behalf of Ed Stone and Lou Friedman, I'd like to welcome you all to today's morning event, which is the short course of the that we have today. The actual workshop starts in the afternoon, and this morning's short course is open to the public and so on. So we have many more people here than at the workshop. I'm really delighted to welcome you here, and I'm really excited about the next couple of days of the workshop. We have a really an exciting program and participants. Another thing to mention that I think Michelle, I don't know if you mentioned or not, but the event tomorrow, there's a event at Caltech at the Beckman Auditorium in the evening that is also open to the public and has been broadly announced. So that's also available for everybody to join. So I will not spend any more time. The actual introductions for each of the speakers coming up, I've asked Lou Friedman to give a brief, just a short introduction. So welcome. I'm delighted to welcome you here to the Keck Institute of Space Studies, and let's enjoy the show. Lou?
Thanks, Leon, and I'll add my welcome too. I'm the at Keck Institute for Space Studies. They have three co-leads. One is from Caltech, naturally, one from JPL, naturally, and one external, which is me, and that's not so natural, but I'm really honored to be part of this group. And I have a really easy job because, at least for the first part of the morning, if you don't know Ed Stone and Freeman Dyson, please leave, because that's my introduction, basically, of them. But I will start with just a couple of words for Ed. Ed, of course, has conquered the solar system with the Voyager spacecraft, leading that as project scientist. He's, of course, been the director of JPL, but he's really the one guy here who represents having gone interstellar, having taken that spacecraft into the interstellar medium, and he's thinking now even more interstellar because his new work is concentrating on the 30-meter space telescope and leading that project here, and professor at astrophysics here at Caltech. Ed Stone.
Thank you, Lou, and welcome everybody. It's 2 years ago was a very exciting time as Voyager finally, at least for most of us, we believe it left the heliosphere and entered interstellar space. I want to tell you a little bit about what the observations for many of you who are part of this. You already know all of this, but there, I presume, are some here in the audience that may not be aware of some of the key aspects of what's been learned in Voyager's reaching interstellar space. This all began back in 1965 when a Caltech graduate student in aeronautics was working at JPL for the summer to look for opportunities to use the flyby of planets to help speed a spacecraft along, and discovered that in 1977, plus or minus a year, you could launch a spacecraft that could actually fly by all 4 giant outer planets. And that's what happened. We started in 1972, launched in 1977, 2 spacecraft, initially to a 4-year mission to Saturn. Voyager 1 headed up out of the plane of the ecliptic, because that's the inclination of the Saturn's rings at the time, and the ring plane. We left Voyager 2 then in the ecliptic on to Uranus, and then finally Neptune, where it flew over the North Pole, which deflected it downward toward Neptune's moon Triton, and it's heading south. So we have these 2 spacecraft, which since 1990 have been on their interstellar journey. This is a plot of the trajectories, at least out through 2000. The main point is here that here's Voyager 1, here's Pioneer 10 and 11, which were launched first. Pioneer 11 is going down the tail of the heliosphere. Of course, neither of these 2 spacecraft, they've been out of power now for over 10, 15 years. Voyager 2, well, with its four-planet flyby, is headed off in this direction and downward. Voyager 1 is upward. We're very lucky that the giant planets, which are aligned this way once every 176 years, were lined up on this side of the sun where the interstellar wind is coming from. And that meant that we were on the shortest way out. And that's very fortunate because we just kind of made it as it is. The other thing I wanted to mention is that there's one more member of this family now, and that's the New Horizons, which July 14th of next year will be at Pluto. And this will be its longitude. You can see very similar to Voyager 2, as it turned out. And it will then be headed off in this direction, hoping to find a Kuiper Belt object that it can fly by, although that is yet to be determined. So those are the missions which are headed out in these different directions, and both Voyager 1 and Voyager 2 are still returning data, and New Horizons will be for some many years ahead as well. These are the teams on Voyager that are responsible for the instruments of investigations. This instruments are working only on Voyager 2, so we don't really measure directly the solar wind, unfortunately. And then we have the two energetic particle instruments, magnetometer, and the plasma waves. I think everybody in this audience knows that the origin of the heliosphere is the solar corona. In this SOHO coronagraph, if you can see, here's the size of the sun. Streaming outward, 400, 600, 800 kilometer per second wind, which expands outward until it finally reaches pressure balance with what's outside. And this is something that Gene Parker, back in 1961, suggested. He'd already predicted there would be a solar wind, and in 1962, Mariner 2, on its way to Venus, actually measured it and said, yes, it really is there, it really is supersonic. But he had already predicted that the wind would create astrospheres, as he called them, or heliosphere in the case of the sun. And in this case, if there was an interstellar wind, it would produce this comet-like astrosphere. So that was known at the time we, of course, began the mission, that we were inside this bubble. The thing we didn't know was how big the bubble is, because there was not a clear, accurate measurement of what the pressure is outside. In 1970, Baranov added the idea that if the wind outside was supersonic, there would be a bow shock outside, as well as a termination shock of the supersonic wind inside. It would be a two-shock heliosphere. And 20 years later, he added the very important concept that there's also interstellar atoms out there, which are neutral, and they also interact by charge exchange with the ions out there, and that can produce a hydrogen wall on the outside, just beyond the boundary of the heliosphere in the nearest parts of interstellar space. So that was about in the early 90s when that work was done. Here's a more modern, up-to-date version of that. And this is not the most current version, but it's a nice, colorful one, an MHD model showing the supersonic solar wind radially blowing, reaching the termination shock where it goes subsonic. It turns and then flows down the tail. And an interstellar wind, if it's supersonic, and now the most recent indications, as I'll tell you, is that it may not be supersonic because the magnetic field is strong enough that the flow, even at 23 kilometers per second, could be subsonic. But if, in this case, there will be a bow wave instead of a bow shock out in front. And this is an area of some current consideration. Here's this is just a cartoon showing the thing which Baranov first calculated, that is the interstellar hydrogen flowing more or less unperturbed, while the ions, of course, are deflected around the magnetic fields that which are part of the heliosphere, and there will be charge exchange. And when that happens, suddenly you have a hydrogen atom moving in this direction, and an ion, which is now, of course, which was a neutral atom, suddenly becomes an ion. And that process builds up a wall of hydrogen outside of 100 AU or more. I'll show you the scale of that wall which is out there. And that's what one sees. This is a HST image of the Ryan Nebula. Here is a bow shock, and you can see the regions of where the charge exchange is taking place and the radiation which results. You can't, of course, see the heliosphere itself or the astrosphere itself. There's another little one up here, too. So these things are really out there, and we're inside, and now finally outside, at least in the bow shock region or the bow wave region. This is another artist's kind of a sketch from Frisch and Huff, and Redfield, who's here, is one of the real experts in this about the larger scale, much larger scale now than what we're done. I'll come back to that at the end here. And so in this case, the relative motion of the sun compared to its surroundings is in this direction, which means that we see a wind coming like that. In addition, this cloud is moving in this direction. And the net result is that it appears the wind outside the heliosphere is coming from this direction and that direction, and that's more or less from the direction of the galactic center. Not precisely, of course, and not from the galactic center itself, but from that region in the sky. And about 23 or 26 kilometers per second, again, this is an area that's somewhat contentious right now as to what the exact speed is of this wind. Some recent IBEX results suggest it's 23, while some older Ulysses results indicate it's 26. And I think that debate still seems to be going on at the last COSPAR. Well, what are some of the characteristics of having left the heliosphere? Inside the heliosphere, the bulk of the plasma comes from the sun, the solar wind, and the magnetic field of the sun is carried out in that. So inside the heliosphere, it's mainly the material from the sun, although those neutral atoms which get in become ionized and get picked up. So there are interstellar atoms inside the heliosphere called pickup ions. Some of the pickup ions, in fact, get accelerated at the termination shock, and there is a very intense population of low energetic particles that fill this region beyond the termination shock out to the heliopause itself. And one of the signatures we were looking for of having left the heliosphere was the disappearance of the heliospheric energetic particles. And here's a plot that shows this is a counting rate scale. This is time. This is the crossing of the termination shock by Voyager 1. You can see these energetic particles peak at the shock and remain essentially uniform, although there was a slight decrease in the last some years out here, 2010, 2011. And here's Voyager 2, which is over 100 AU away, and almost exactly the same feature. And once it crossed the termination shock, it had almost exactly the same intensity. And we'd seen that intensity on Voyager 1 for almost 7 years until 2 years ago when they disappeared. Basically, in one pass, they were there from the DSN. Next day, when we got our next DSN pass, they were gone, and they haven't come back. So the energetic particles are clearly, the heliospheric energetic particles are depleted, and that happened, durably happened. There were some precursors, as you can see, but it durably happened on August 25th, 2012 at 121.6 AU. We believe, although not everybody agrees with this, but I think most of the team feels that this is one of the key signatures of having entered interstellar space. Another key signature had to do with the galactic cosmic rays, which are outside. Now, outside the plasma comes from the explosion of supernovae, of other stars, not from our own sun. The magnetic field is the magnetic field of the galaxy, which is in fact carried by the plasma that is ejected by the supernovae. And the most recent batch of supernovae occurred in the nearby association, OB association, on the order of 5, 10, 15 million years ago, relatively recent on the galactic time scales. So the galactic cosmic rays are outside. Of course, the highest energy ones, those moving with nearly the speed of light, or can be observed clearly in here at Earth and were discovered over 100 years ago. But those with less than about half the speed of light cannot get in. The wind from the sun, the magnetic field carried by that wind and the turbulence basically excludes the low energy cosmic rays from entering. And And so one other key signature was that we would see the highest peak intensity of cosmic rays at low energies yet observed. And that would be basically reasonably steady once we got out there. So here's an integral counting rate of particles with energies greater than 70 MeV. This is a typical counting rate when there's minimum solar modulation during periods of low solar activity and low modulation of the galactic cosmic rays. And for about the first, well, so 2003, this is the Voyager was at 90 AU in 2003, still inside the heliosphere. In fact, it had not yet reached the termination shock of the solar wind yet at that time. And a rather small gradient in intensity, not even a factor of 2 increase in intensity. These are the solar maximum periods which modulate the cosmic rays. You can see the solar cycle basically. You can see a very slow trend of increase. And then once we crossed the termination shock and reached the heliopause, the intensity rapidly increased, and then 2 years ago jumped up to this level right here. And so the intensity outside, once we reach interstellar space, about 75% of this intensity does not reach 1 AU. That's kind of the increase, that's the shielding effect, if you like, of the heliosphere. And much of that shielding, most of it, in fact, takes place in the region between the termination shock and the heliopause itself. So what are the cosmic rays really constant now outside? Well, there are models that suggest that even outside the heliopause, this is the heliopause, and this is the intensity. You can see inside the heliopause, in the heliosheath, a very steep gradient. But even outside, there's a small gradient predicted by this particular model, Strauss et al. Now, this is a very controversial area in the sense that others claim that, in fact, there really can't be any gradient out there. And so measurements will, in fact, be part of this determining that argument. But we obviously are looking to see if there is a small gradient. This is not a large predicted gradient. You can see the total gradient is only about 40% over roughly 100 AU. So it's not a large gradient. And it may be a while before we can sensibly measure it, but I'll show you what we know right there. This is what we've got. This is the greater than 70 MeV. Here is the heliopause, and we have no measurable gradient for the last 2 years. We do see 2 transient increases, and I'll come back to those a little bit later. These are the electrons, the cosmic ray electrons, very small gyro radii, very, very easily modulated, but essentially no gradient measurable. So far it looks as though we have reached the steady state galactic cosmic ray. And here's what the spectrum looks like. MeV per nucleon. This is what we were seeing inside with the heliospheric particles dominating the intensity, as you can see, by several hundred above what it is now. And this is what we're seeing outside for the hydrogen and for the helium. As I said, all the observations below this energy could not be made inside. All of this data can be acquired only when you're outside the heliosphere, because these cannot sort of diffuse inward against the outward motion of the turbulent solar wind. And there were lots of models, predictions as to what we might be seeing outside, and there were even suggestions there might be a nearby source of particles outside, or maybe even our own heliosphere was the source of these particles, and we see those outside. Turns out we don't see any no nearby source of low energy particles, and all we see are these very flat spectra. And to comparison, this is the peak in the energy spectrum seen at 1 AU, and you can see it peaks at around 200 MeV per nucleon. Outside, it's more like 20 or 30 MeV per nucleon, a factor of 10 lower energy, and a factor of 10 higher intensity outside at these lowest energies. And we can now begin to do this for all of the elements, although you can see the statistics are not great. The red data are the data Voyager is taking. The blue is what's seen at 1 AU. And you can see that we're beginning now to determine the spectra with some detail for all the elements lighter than iron. What about the magnetic field? The coordinate system is this. That is called the RTN coordinate system. So if your spacecraft is here, R is outward, T is in the tangential direction, longitude in other words, in longitudinal direction, and N is in the northward direction, like as it is on the Earth. This is an RTN coordinate system. This is what we expected. That is, if we're looking outward, and so here's the T in this direction, longitude, here's the northward direction, and we expected that the local interstellar magnetic field just outside would be off in this direction as compared to the inside field, which would be in the T plane, because it's just the spiral field of the sun being carried out. That's what we expected before we got there. What we saw is this. This is the magnetic field. This is the intensity of the field. Here's the August 25th date. You can see the intensity is, there are some transients, but once you get away from the transient, the intensity is about 4.6 microgauss. A very relatively strong field, which is the reason there's now a question about whether there's really a bow shock or not. You can see the direction. This is the direction of the inside field will be in longitude, will be either be at 270 or 90, depending on what the polarity is. It's either this way or that way, but it's in the T direction, plus and minus. But you can see that there is in fact an offset. And now that we're outside, it's about 20-some degrees different than that. And if you look at the latitude of the field, which should be 0 on the average, which it was when we were inside, although clearly there are disturbances which propagate out, which complicate this. But once we got outside, the field is the quietest, smoothest field. There's no measurable turbulence. I mean, in other words, it's not that there isn't any, it's just that with our instrument, this is the quietest field that we've seen since launch, with no measurable turbulence. And you can see the direction is remarkably steady. And this is just that galactic cosmic ray intensity I showed you, showing this is where we, August 25th, when we finally entered interstellar space, 2012. So the field is somewhat stronger than was typically expected, more like maybe 0.2 or 0.3, 2 or 3 microgauss. It turns out it's about 4.6 microgauss, and again, reasonably steady at this point. And so instead of seeing this, what we saw was that the field outside is almost the same as the field from the sun, and very similar to the field that we were seeing just before we finally crossed on August 25th. And this is an area also that's currently this interaction, the detailed physics of the transition from inside to outside, and the dropouts, which we saw, are things which are currently actively being studied. Here's one thing which Maraf Ofer and her group have done to try to understand the direction of the field. We believe that, in fact, based on various kinds of data, that the interstellar field, we're looking from the outside toward the nose of the heliosphere, is inclined like this. And yet what we found was the field just outside the heliopause itself is in this direction. And so in this particular model, what they've been able to show is that because the plasma is deflected around the outside of the heliopause, that twists the field, and it just happens that we may well be in a region where the twist is just twisted it so it's almost in the T direction, so it almost is in the direction of the solar field inside. But this again is an area that's currently being looked at very carefully to see if one can better understand the details of this interaction of wrapping this field around the surface of the heliopause. But this also means that as we move further away from the heliopause, one should see the field tip like this. We should see it gradually change. And so that would be another key thing that we'll be looking for in the years ahead. Another thing which we managed to measure was the density. We don't have a solar wind instrument, so we can't measure the solar wind itself directly, but we occasionally can measure the density of the plasma, the electron density of the plasma. And inside, where it's solar material, the density we know, we measure it. It's on the order of 10 to the minus 3 per cubic centimeter. Outside, it was expected that the interstellar density would be less, 10 to the minus 1, but it's cold. I mean, inside it's hot and low density, outside it's somewhat higher density, although of course it's still very tiny because it's very cold. That's what we expected, and we do have a plasma wave instrument which can look at the electron oscillations when there are oscillations. And we hadn't seen any oscillations since we crossed the termination shock in 2004. And yet, fortunately, the sun cooperated, had a coronal mass ejection, had actually a series of coronal mass ejections in 2012, which a year later got to where Voyager 1 is and actually caused the oscillations. And this had been observed before, starting back in 1982 or 83, when we just passed Saturn and got far enough out that the kilohertz radio waves from out there could propagate inward, and one began to see these bursts of radiation. I think Ralph was one of the first people who thought about the origin of these things in the outer solar system coming from interstellar space and occurring whenever there's a large blast wave. It's indicated by these spikes, rapid decreases in cosmic rays associated with these blast waves. And so these features had been discovered, and their prediction was that these emissions were occurring in the interstellar space because the frequency was too high. The frequency was kilohertz, meant the density was 10 to the minus 1 rather than a few hundred hertz, which would have been what it should have been, which it was inside when we saw them. So there was evidence that there were events causing plasma oscillations outside. They lasted for a very long period of time. This is from 1992. And it also had a increasing character and frequency, suggesting that as the blast wave propagated out, or tsunami wave propagated out into interstellar space, it was propagating into an increasing density, plasma density. And so this is the simplified model of the density profile, 1 over r squared inside, the termination shock, heliosheath, the heliosheath, and then here's the heliopause, and there's the ramp with a kind of a wall associated with this hydrogen wall, which I mentioned earlier. These two features are two blast waves, two global merged interaction regions that were a series of coronal mass ejections, which about a year later, 400 days later, finally reached Voyager. Some happened reached Voyager in 2013. And then again, earlier this year, there was another episode. And the frequency was, in fact, kilohertz, just as was expected from the radio emission. But these were, in fact, oscillations locally at location, and told us the density was 10 to the minus 1, not 10 to the minus 3, and that we indeed had entered interstellar space back in August of 2012. And we saw the plasma ramp, which had been predicted we would see, and of course the question now is, what's the evolution of this going to be? The most recent set of observations suggest we're still in this range of densities, and that's what's being worked on right now. Hopefully at the AGU meeting we'll have an update on this most recent event. So there's some puzzles. Why is the heliopause so close? What is the extent of this plasma ramp? Will the field direction rotate as we move further upstream? Or will we, in fact, see another current sheet because we're still inside, which is a model that Fisk and Gleckler have really suggested we would see another sector boundary, basically, because we were still inside, although I think most of us believe we're really indeed outside. Another new piece of information I see red lights on is the energetic neutral atoms, which are coming from out there, and which have been now mapped extensively by the IBEX mission. And that's also produced the surprising fact that there's this ribbon of enhanced neutral atoms coming from out at the edge of the heliosphere, and which seems to be organized by the general direction of the interstellar magnetic field being inclined, as I showed, but I think, again, there's a lot of debate about the exact mechanism and of this region, which is presumably just beyond the heliopause and extends some distance into the nearby interstellar medium. Just let me wrap this up by saying that here's what the plasma density looks like in a recent model by Hercules and et al. And the hydrogen wall, in this case the plasma density, you can see it peaks, but you can see the scale is a few hundred AU. In this case, there's a bow shock. In this case, with a strong magnetic field, there's no bow shock, just a gradual increase in the plasma density. The neutral hydrogen density looks similar, depending on the strength of the interstellar magnetic field. And I say our measurements suggest we're really more like this than we are like that in terms of the density of the hydrogen of the wall. But you can see the scale, which is on the order of several hundred AU. And Voyager, the arrows which I put here, are the places where Voyager 1 will finally run out of power, somewhere right about there. So we're just barely beginning to end, we'll be just barely getting into this region when we finally run out of power. So with that, Voyager continues. Thank you.